Review of literature. What is mentioned in the previous sections dictates the necessity for soil erosion quantification and highlights soil erosion modeling as the utmost vital action taken, in the context of an integrated management at the basin scale. Soil degradation by accelerated erosion is a serious problem and will remain so during the 21st century. Soil erosion prediction and assessment have been a challenge to researchers since the 1930s, and several models have since been developed. However, the treatment of soil erosion in the form of soil conservation plans has made its appearance long before that, in the early 19th century. As stated by Dotterweich, the first extensive essay on soil conservation known to the Western world was published in Germany in 1815, while the rise of professional soil conservation occurred in the late 19th and early 20th centuries. Substantially, the first decades of the 19th century can be considered as the outset of the profound understanding and studying of the phenomenon of soil erosion. It is remarkable that the third President of the United States, Thomas Jefferson, in one of his letters in 1813, demonstrates his awareness of the on- and off-side effects of soil erosion, the role of runoff in soil erosion, and the interaction of soil conservation, hydrology, and crop production, important scientific topics today in understanding, predicting, and modeling soil erosion, 200 years later. The most significant, and groundbreaking for that time, theory regarding soil erosion was introduced in 1899 by Davis. His theory, known as cycle of erosion, is an idealized model for stream erosion and landscape development in which stream erosion occurs in a gradual sequence of stages: young, mature, and old. During these stages, the soil surface erodes up to the point it becomes a peneplain. Davis's cycle of erosion dominated in geomorphology for more than half a century. After 1950, the division theory began to be questioned. Among those who challenged it was Chorley, who rejected the division cycle of erosion and suggested a quantitative method based on general system theory and numerical modeling. King has also tried to dispute the division cycle of erosion, however, his theories did not manage to escape the division cyclical nature. According to Bishop, the dissatisfaction was embodied in Strahler's call for radical change and the embracing of a new approach and underpinning concepts, ultimately taking the discipline into spatial and temporal scales much reduced from the grand vision and sweeping canvas of Davis and his disciples. Strahler's call is now being heard in long-term landscape evolution as geomorphology embraces quantitative and geochemical analytical approaches to the sorts of questions that Davis sought to address. Boardman highlights some of the most notable and influential advances of the recent past, among which are the following: Trimble, with its emphasis on sediment storage and the relationship between erosion on the hillslopes and the role of the valley bottom stream; Govers and Poison's empirical study of rill and interral areas; Deploy's attempt to categorize eroding Western European landscapes, and Blakey's recognition that degradation occurs because of people-land relationships often involving social and economic opportunities and constraints. The Universal Soil Loss Equation, USLE, is one of the most significant advances in soil and water conservation in the 20th century. It has been applied in almost all the kinds of climatic conditions and types of soils around the globe, as an individual model, while it also constitutes an important component of many models and hydromorphological softwares. Since then, there have been many parallaxes and modifications of USL, the most known of which are the Modified Universal Soil Loss Equation, MUSL, and the Revised Universal Soil Loss Equation, RUL. The evolution of the soil erosion and the sediment transport modeling has consistently followed the evolution of technology. In the last few decades, there has been a hectic advancement in the domain of soil erosion modeling, as a result of the advancements in computer science. This resulted in the development of a plethora of integrated models that, in many cases, fully address the study of the hydromorphological processes. There is a wide range of integrated models that simulate the runoff, the soil erosion, and the stream sediment transport processes, on a continuous, long-term, or on an event-time basis. Some notorious examples, with a prominent position in literature, are the following: the Agricultural Non-Point Source, AGNS, model, the Chemical Runoff and Erosion from Agricultural Management Systems, CREAMS, model, the Aerial Non-Point Source Watershed Environment Response Simulation, ANSWERS, the Soil and Water Assessment Tool, SWAT, the European Soil Erosion Model, Eurosum, the Hydrologic Engineering Center Hydrologic Modeling System, HEC-HMS, and the Watershed Erosion Prediction Project, WEPP. These models have been applied both standalone and as a part of integrated mathematical models, to model the sedimentary cycle.